Right. Calculus 1. Chapter 5, integration. I just trying to organize, clear up some thoughts here. When this chapter started, so these are more ideas, but I'm kind of in 5.4 with some of these ideas. But when this chapter started back in 5.1, we were doing an indefinite integral. So we were just trying to learn how to do an antiderivative, and we would get this antiderivative plus c. And that was a whole, and when you have this plus c, it's like a whole family of functions. I don't know if I ever said it like that, but let's just say the answer was x squared plus c. That's a whole bunch of functions. It's depending on what c is, it's like a whole family of functions, of parabolas in this case. So that's an indefinite integral. Then we proceeded to learn about a definite integral, which is from a to b, and then you find the antiderivative, and there's no reason to put the plus c. Some of you were doing that, I noticed on your quiz, but you don't need the plus c in this. Now you evaluate from a to b, and you plug in the b, you plug in the a, and you get this number is what you get. I had one video where I said, that could be a positive number, could be a negative number, could be 0 actually. So when you do a definite integral, you get a number. And we learned that you could call, what does that number mean? You could say it's the net area between the function and the x-axis. We talked like that one day. Or just the area under the curve, we would loosely say, but to be more specific, maybe it's the net area between the function and the x-axis. But it's a number. When you do a definite integral, you evaluate and you get a number. But here's this new thing in 5.4. There's this way to talk about a definite integral as a function. So this is because you're going from a to a variable x. And because you're going from to a variable x, the variable of integration has to be different, so that we'll use t as the variable of integration. So notice what you do. You get some function of x. You would integrate, you'd get some answer in t's, but then you'd plug in a variable x and a number a, and you'd get some function of x. And so this is kind of funny to have this variable as part of your bounds of integration. Instead of numbers, where you get a number, you get this variable x, where you get a function of x. And you could call it an accumulation function. What you could think of it as, and we'll do an example here, an accumulation function. You're accumulating the area under this curve as you go from some starting point, to some variable x. So I want to do an example of that. So I made up this problem. F of x is this accumulation function from 0 to x of 2 plus sine x dx. Oh, oops, hang on. When that variable up there is x, I can't use x down here. That's not right. So we'll do t's down here. Yeah. And so just to illustrate what this is, like I said, it's sort of, I could think of this as the area under this curve. This is a 2. I think this is a sine function. 2 plus sine t. I'm integrating from 0 to some variable x. If I stop right here, it's the area under the curve from 0 to x. If x keeps moving, it's accumulating more area. It's accumulating more area as that variable x moves down the x-axis. So you could think of it as the area up until that point, but if that point moves, you get more area. You accumulate more area. You can do it. Let's do the integration. You get 2t. When you integrate with respect to t. When you integrate a sine, I think you get negative cosine. I think that's right. And then you're going to evaluate from 0 to x. And this will be your accumulation function. Now be careful, watch what happens. You plug in the x for the t, so you get 2x minus cosine of x. Now you plug in a 0, a lot of times we get 0 when we plug in a 0. Not on this one, watch this. When you plug in a 0, that's a 0. but the cosine of 0 is not 0. The cosine of 0 is a 1. So this accumulation function becomes 2x minus cos x minus a negative 1. That's going to be plus 1. So this is this new function we created, and I can call it an accumulation function. It's accumulating area. If I want the area from 0 to 2 pi, I could do the integral from 0 to 2 pi, but I've done the integral, and now I can plug in a 2 pi. Let's just try that. If I wanted f of 2 pi, I would plug in a 2 pi. The cosine of 2 pi is a 1. That's a negative 1 plus 1. That would sort of cancel. I'd get a 2 pi here times 2. I think the answer would be 4 pi. What is that? 2 pi, that would be, hang on. That's 2 pi right there. So I just found that area. Must be 4 pi. Huh, interesting. What if I wanted to go to 3 pi? What's f of 3 pi? I'd accumulate more area, I guess. I'd plug in a 3 pi, I'd get 6 pi minus, okay, hang on. The cosine of 3 pi is a negative 1, so minus a negative 1 is plus 1, plus that other one. I think I'm getting 6 pi plus 2. So I got that number. I'm accumulating more area if I go to 3 pi. Where's 3 pi? I think 3 pi would be here. Here's pi. 2 pi, 3 pi. So I just accumulated some more area. Anyway, that's that. And what follows out of that is what's called the second fundamental theorem of calculus. This is just in general. If you take the derivative with respect to x of this function, because now remember this is a function of x. Now I'm talking in general, of f of t dt. So this is some function of x. If you take the derivative of this function of x, it's pretty easy. You know, it's kind of like you're taking the derivative of an integral. The derivative and the integral should cancel each other out. I mean, in other words, you do the antiderivative, then you take the derivative of that. So you're back to this function. The answer is f of x. And that's the second fundamental theorem of calculus. Let me just see if that would work. If I took this derivative, what would I get if I took this derivative? I'd get a 2 plus sine x, and that would go to 0. So I think I'd get 2 plus sine x. 2 plus sine x. When you take the derivative of this integral function, you just get this. So again, that's called the second fundamental theorem of calculus. And I think I'm done with ideas in 5.4. I didn't assign much of that homework. I didn't assign too much of this homework. There's a little bit of that. As this chapter moves on, we move into 5.5. We do some good stuff. It takes a little more focus. It takes a little more challenging. At the end of this chapter, we do some changing of variables. We call it U-substitution. So 5.5 is real important. That'll be the next video. Thank you for your hard work.